So welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. This week we work on continuum models, and now that we have derived the field equations, we can look at solution types. So here's an example taken from a simulation. We put the extended neural population on a ring. So we close it down, and then this is my X. And we want to use the version with local excitatory interaction and long-range inhibitory interaction with a certain set of parameters for the interaction weights between the different neurons. And what I find is that as a function of time, the activity looks pretty much constant, and as a function of space, it looks also constant. So this is a first solution that we call the homogeneous solution, because it has no spatial structure, and it's also the input-driven regime. And then for the same model, just with a slight change of parameters, there's also a second solution where, again, as a function of time, there's hardly any change, but as a function of space, I now have a very sharply peaked profile at a certain location. The medium would be roughly here. So this is a peak or bump of activity centered just above x equals 0. So we can look at both solution types, and for the moment I focus on this type A, which means a homogeneous solution. And the homogeneous solution means that if I have no input, then the activity would just be flat. So there's no spatial structure. However, if I apply an input, like the input here, then I would see an activity profile which has peaks at the corners of my stimulus and which is overall elevated in the regime where the stimulus is applied. So this regime typically occurs if my connectivity profile for the weights has a structure. So here's the size of the weight, and this is x minus x prime. That's the distance between the two neurons. It has sort of this broad profile, and the amplitude is rather small, so it's called a weak lateral connectivity profile. Now the other solution is the bump solution. And here, in the absence of any input, even for input 0, I can find an activity peak that's very strong around a certain location and say, this is my location x0. Now, this location is arbitrary. The activity profile could also sit at any other location. It could sit here, or it could sit there, or it could sit there. So I have a translation invariance, but the shape of the profile is always the same. Now, this kind of bump formation might be very useful for spatial working memory, in particular heteroaction cells, and we'll look at this in part 7 later this week. So far I just had schematic figures. Now here is such an activity profile in a bump solution for a network of generalized integrated fire neurons, exactly the type of neurons that we have seen earlier this week. The dots here correspond to simulation results. It's the activity A as a function of the location X, or we can interpret this as the preferred orientation of cells in visual cortex. Now the solid line corresponds to a solution that's calculated from the field equations. And you see that the simulation nicely matches the solution of the field equations for this bump solution. I already mentioned the Mexican head profile with local interaction and further out inhibition. Now to get the bumps, on the previous slide, it was a very large peak compared to the one we had earlier for the homogeneous solution, and then it continued, the inhibitory part continued to both sides over a very long distance. In fact, infinitely long. And in this case, the bump solution is a single bump. However, if you have an activity profile like the one indicated here, where the inhibition also has only some finite range, then it's possible that as a function of space, multiple activity bumps will form. So what we see here is the time axis, here is the space axis, this is the space axis, and we see that several bumps, one activity bump sits here, the next one sits here, the next one sits here. Intuitively, if the interaction profile, the W of x minus y, falls off at some distance, here a distance of 5, then it's possible at a distance of 10 to have the next activity bump. Now in this case, for this dashed line here, for the same interaction profile, and for a weak input, we find that there's the homogeneous solution. If you have a somewhat stronger input, then these multiple bumps evolve as a function of time and become stable solutions. If the external input is even stronger, the bumps remain, but they get a little bit broader, and for super strong input, it's just a very high activity state, a homogeneous high activity solution that is stable. So, let me sum up. The field equations have two types of stationary solution. There's a homogeneous solution, which means no spatial structure, and this occurs in the absence of input or for flat input, when the input has no spatial structure. And then if the input develops a spatial structure, then the homogeneous solution becomes inhomogeneous and it responds to the input. And we have seen one of the features is a contrast enhancement. Now, the other solution is that even in the absence of input or for flat input with no structure, spontaneously a bump forms. This is my bump profile. Now, if I have an input, then the bump would occur at the location where the input is. So if I initialize here by putting an input pulse at this location, then the bump would appear around here. If I initialize somewhere else, the bump would sit over there. So we have these two different solution types. Both are stationary solutions. Both can be stable solutions. In the next two sections, we are going to apply these different solution types to cognitive and perceptual phenomena. But before we go there, please take your time and have a look at the quiz.